We're going to look at what are called indefinite integrals. This is just another way to say that what we want to do is find the general antiderivative. All right, so what are the pieces here? This is called the integral symbol, and we'll learn a lot more about it soon. All right, this piece is called the integrand. All right, and it's the function that we want to find the antiderivative for. All right, and this piece, all right, is part of the integral symbol. It goes along with this. All right, we'll see a little later in the chapter where this comes from. But what this together means is that we want to find the antiderivative of little f. So we want to find a function, we'll call it big F, whose derivative is equal to little f. Okay, so this is the same thing we've been finding in chapter 4. All right, we want f prime of our antiderivative to equal little f. All right. So some examples. All right. This is just our power rule, all right, which means we're going to add 1 to the exponent and then divide by that new exponent. Okay. So the dx here just kind of disappears. It's part of the symbol, all right, that tells us to take the antiderivative of x squared. And I want you to make a habit of keeping that symbol along, even though it doesn't appear to do anything. All right, as we'll see later in this section, it's essential for figuring out how to do some of these antiderivatives. The antiderivative of 1 over x is the natural log of the absolute value of x plus c. All right. These absolute value symbols here are essential. 1 over x is defined for all numbers but 0. Natural log of x, if I left off the absolute values, would only be defined for positive x. This extends it to all reals except 0, just like 1 over x. So what we're doing here is getting these to match. So the absolute value symbols are key. Right, how about this one? We saw something like this in class the other day. Right, this looks like somebody came along and differentiated by the chain rule. Right, I see x cubed here, and I see the derivative of the inside. Right. And you may be able to just spot that the antiderivative here is sine of x cubed. Right. And I need the general antiderivative, so plus c. Right. So what we had to do there was undo the chain rule. Sometimes that can be tricky, right, if we can't just spot what to do right away. In this video, we're going to see a technique called substitution for figuring out how to undo the chain rule. Now, if you're uncertain if this is correct, the nice thing about taking antiderivatives is you can always check your work. All right? So to check, if I take the derivative of the right side, right, I should get back to here. So the derivative of sine of x cubed is cosine of x cubed times the derivative of the inside plus the derivative of a constant, which is 0. Right? So in fact, I know that this is the general antiderivative because if I differentiate it, I get back to where I started. So we've done that correctly. Right. Much of what we want to do in this section is figure out how to undo the chain rule. Remember the chain rule. The chain rule says the derivative of a composite function, I have an inside and an outside function, as the derivative of the outside function, leave the inside alone, times the derivative of the inside function. All right. Every differentiation rule is also an anti-differentiation rule. The derivative of this is equal to this, so the antiderivative of something like this is equal to f of g of x. Right. So the chain rule written backwards just says if we want to find the antiderivative of one of these chains like this, we're going to get back to the original composite function. Right. And then in the general case we have a plus c. So going this direction we have the chain rule. Going this direction we're undoing the chain rule. Right. But sometimes it can be tricky. Right, so what we're about here is to see a technique for kind of keeping track of the bookkeeping we need to do in order to undo the chain rule. That's what substitution really is. All right, it's a little cumbersome at first, and it may be awkward, but we'll get used to it. All right, when we're dealing with the chain rule, we're interested in what's the inside function and what's the outside function. When we want to undo the chain rule, a good place to start is by looking to see if you can identify what is an inside function. Right, there's an inside function. It's embedded inside of another function, in this case cosine. Right, I'm going to give that function a new name. This is called the inside function. I'm going to give it a new name. Right, so I've called this piece u. Right, now we're going to compute the differential. Right, and if you don't remember how to compute the differential, right, if we have y equals f of x, then dy is equal to f prime of x times dx. All right, that's differentials. So what we're going to do here is compute the differential du. So du is equal to the derivative 3x squared times dx. Well, notice this is du. Right, so these two pieces together make up du. So what we're going to do is substitute u and du into this integral to help us find the antiderivative. So our integral now is equal to cosine of u, all right, that's this piece, times du. Well, look at this. Now this says we need to find, written in this new variable after we've substituted, we need to find the antiderivative of cosine of something simple. The antiderivative is sine of u plus c to get the general antiderivative. And now what I want to do is undo my substitution. Okay, I started with an answer, started with a function in terms of x. I want to finish with a function in terms of x. All right, so remember, u is x cubed. This is just a good way to take care of the bookkeeping associated with undoing the chain rule. All right, so our final answer, I'm going to rewrite it. We've already seen this fun. I call this one a type 1 substitution. It's type 1 because what we chose to substitute, u equals x cubed, right? When we take du, it exactly fits with everything else that remained in the integral. We didn't have to make any adjustments. Right? So I call this a type 1. So u and du fit exactly. Right? After I choose u and compute du and make the substitution, there are no x's left over. Nothing's left to adjust or fix. Right? That doesn't always happen. And we'll learn how to deal with that when we get to it. All right, let's try another here. Okay. So I want to look for a function inside of another function. This looks like perhaps it could have come about by differentiating something using the chain rule. Right. So the function that's inside another function, in this case, is square root x. So I'm going to let u equal square root x. Remember, we're just doing bookkeeping here. Right. Another way to say that is x to the 1/2. So now compute the differential. du is 1/2 x to the minus 1/2 dx. Or that's another way to say 1 over 2 square root x dx. Okay. So du is exactly the bits in green here. Here's du. So I can rewrite my integral as equal to e to the u is square root x, times du. All right. So now this just says find the antiderivative of e to the u, and I know how to do that. It's e to the u plus c. And now at the end, I need to convert my answers back to all x's, so I get e to the square root x plus c. So again, this was what I call a type 1. You're not going to find type 1 and then later type 2 and type 3 talked about in any textbook, but they're a good way to kind of think about and maybe give names to some of the kinds of substitutions we're going to make. Right? So this is type 1 because after I picked u, du was exactly what I needed. Right. Here's another example. Now this is one where it may not be quite as clear, right, what to substitute, all right, what to call u, because I don't really have an inside function here. I really have a ratio of two functions. All right. The only bad substitution that you can make, all right, they're not all good, but the only bad one to try is to just call u equals x, because all that's doing is renaming the variable. All right, so that doesn't do me any good here. But I could try u equals natural log of x. And that's a very good thing to try because when I take the differential, I get 1 over x dx. Okay, so du is equal to 1 over x dx. So starting with my integral here, I'm going to rewrite it just to make it absolutely clear if I can. So I have here u and du. So let's write that. Now the idea is that I should have something simpler to find the antiderivative of. 1/2 u squared plus c. And at the end here, what I need to do is put back my x's. So I know u is natural log x, so I'm going to write that here. I get 1/2 natural log x squared plus c. If ever you're uncertain that you've done something correctly, or if you look at your answer at the end and you just don't buy it, take the derivative and see if you get back to where you started. So to check, that's why I love doing these, because it's just so easy to check our work. Right, I'm going to take the derivative. All right, so now I have to do the chain rule, and you're always going to have to do the chain rule on these. That's why we do substitution. So I bring the 2 to the front. I'm going to leave the 1/2 alone here, times 2 natural log of x to the 1 times the derivative of the inside, 1 over x. The 2's cancel, and I'm left with natural log x over x, which is in fact the function I started with, whose antiderivative I wanted to find. Right. So again, this was type 1, because after I picked u, du was exactly what we needed. So let's write that, type 1. Right, now we're going to move on to the next level of difficulty, which I'll call type 2. Right. Type 2 integral is when, or type 2 substitution is when you make the substitution and then you find the differential, and the differential doesn't quite match what you had. All right, so let's try it here. I'm going to look for an inside function. There it is, u equals x cubed plus 4. Calculate the differential. Du equals 3x squared dx. Well, here's sine of u, and so what's left over I would like to be du, but it doesn't quite match. I have du as 3x squared dx, and all I have left over here is x squared dx. Right. So in a type 2, we have to make a numerical adjustment. I'll just say we have to adjust du to make it fit. And this is usually just a numerical adjustment. All right. So if I multiply both sides by 1/3 here, I get 1/3 du equals x squared dx. All right. So 1/3 du is exactly what I need to make the substitution. All right. So now let's do that. So my integral becomes, in the new variable, the substituted variable, x squared dx is 1/3 du. And it's conventional to put the du down here, but you don't really have to. Right? And then sine of u. Right. Now antiderivatives, just like derivatives, you can kind of pull multiplicative constants out of your way. So the antiderivative is 1/3 times minus cosine of u plus c. or minus 1/3, putting the minus out front here, cosine of x cubed plus 4. All right, and then to get the most general antiderivative, I've got the plus c out here. Did we do it correctly? Well, check, 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 check your work. Take the derivative of your answer. I can ignore the plus c at this stage because, of course, the derivative is 0. Pull the minus 1/3 out of the way. Take the derivative of cosine of something as minus sine of that something times the derivative of the inside. That's the chain rule. Minus minus gives me plus. 3 times 1/3 is 1. And we're just left with the sine of x cubed plus 4 times x squared, and that's exactly where I started. So we found a good antiderivative. Type 2 is when you have to make a small adjustment to du to get it to work. All right, here's my inside function. So u, calculate the differential. And I really do want you to write du and dx wherever they're as part of the integral symbol, because that helps us keep track of the bookkeeping for making these substitutions. Right. So du is not quite what I need. I need cosine x dx, and I've got 5 cosine x dx, so we make a small adjustment. We multiply both sides by 1/5. And now we're good. 1/5 du is exactly the piece that I need. So I can rewrite this as the square root of u times 1/5 du. The 1/5 I can bring out front. In fact, I'm going to write it all the way outside the integral symbol because it's just along for the ride. So this is u to the 1/2. The antiderivative will be u to the 3/2 divided by 3/2, or times 2/3. The 1/5 is still there, plus an additive constant. So we have 2/15 u to the 3/2 plus c. But u is really 5 times the sine of x plus 5. Right. Again, if you're ever unsure, take the derivative and see if you get back the original integrand. Right. It works in this case. I'll let you check it. One more type 2 here before you, or maybe we'll do a couple. All right. What's inside? Well, 3x is inside the exponential. It's the exponent. So let's call u equal to 3x. du is 3dx. So I see here I've got e to the u, and du doesn't quite match what's left over, which is dx. So I'm going to adjust it. 1/3 du is equal to dx. And now I can make the substitution. I get e to the u times 1/3 du. What's the antiderivative of e to the u? It's e to the u. 1/3 along for the ride plus c. And this is equal to 1/3 e to the u was 3x, so I'll put it back, plus c. All right. So in some ways this is a bit mysterious, right? But substitution is a technique for undoing the chain rule. When you differentiate this answer at the end here, you're going to require the chain rule to take the derivative, and that'll take you back to here. Now with exponentials, there's often a second kind of substitution that will also do the job. So let's rewrite this. And that is, instead of taking u to be the inside function, I can take u to be the whole exponential, which seems very strange. Then du is equal to e to the 3x dx times the derivative of the inside here, which is 3. So 1/3 du is equal to e to the 3x dx. So 1/3 du is exactly my whole integrand here. So this is equal to the integral of 1/3 du. Alright, so this means I need to find the antiderivative of 1/3 with respect to the variable u. Well, that's just 1/3 u. Alright, the antiderivative of the number 1 is kind of hidden here if you like, is u plus c. Right? And what is u? It's e to the 3x plus c. Alright, so now we're back to the same answer that we got previously. So two kinds of substitutions that can make that happen. There's frequently more than one way to do these things. Right. One more type 2. It's type 2 because after you calculate the differential, you have to adjust a little bit to make it fit. Right. Well, what am I going to do here? I don't know any function whose derivative is tangent, so I don't know a direct way to find the antiderivative of this. Okay, so sometimes when we have trig functions, a useful trick is to rewrite them in terms of sines and cosines. And I can do some substitution here that will help. All right. When you're thinking about what can you substitute, what can you call u, all right? Well, I'm going to take u equals cosine x, because I also see the derivative of cosine in my problem. Right? The derivative of cosine is minus sine of x dx. So we calculate the differential. Well, that's not quite what I need. Du is minus sine of x dx, and I don't have minus, I just have sine of x dx. So adjust it, multiply both sides by minus 1, and now rewrite using the new variable. So cosine of x, that's u. Sine of x dx is minus du. This looks kind of awkward, so we're going to rewrite it. The minus I can bring clear out front, it's just along for the ride. I'm going to rewrite this as minus 1 over u du. Now I can anti-differentiate. I've already kind of undone the chain rule step. So the antiderivative of 1 over u is the natural log of the absolute value of u plus an additive constant to get the general antiderivative. And now at the end here, we put our answer back in terms of x. Well, u is cosine x, so I get minus the natural log of the absolute value of cosine x plus c. Now, if you look in a table of integrals, or table of antiderivatives, that's probably not what's going to be listed for the antiderivative of tangent. It's right, and you can check, right? But it's probably not what's going to be listed. Usually, they do a little trick. Since you've got the number minus 1 in front here, they'll put that up here on the exponent. That's the same thing as saying the natural log of 1 over the absolute value of cosine of x plus c, or the natural log of the absolute of secant x plus c. Same thing. And that's usually what you'll see listed as the antiderivative of tangent. But that's just algebraically equivalent to minus the natural log of the absolute cosine. All right. That was type 2, because once we got u, du did not quite fit exactly, and so we had to make a small adjustment. All right. The last and most difficult of these are what I call type 3 problems. Let's just try this, and we'll see where we get stuck, and that's why we're going to call it type 3. You'll see. All right. So I look for an inside function. Here it is. So I'm going to call u equals x plus 4. So here's u. Then I calculate the differential. Du equals the derivative 1 times dx. So du and dx are the same. So here's du. So I've got square root u and du. What about this x here? What am I going to do with that? All right, it's not covered by u. It's not covered by du. So I have this extra bit here. All right. I call these type 3. Right? We have to reuse the substitution in this case u equals x plus 4, in order to address other parts of the integrand. So we have to reuse the substitution. What do I mean by that? All right. Well, I can write this x here in terms of u if I go to my substitution and solve for x. So I get x equals u minus 4. So this x right here I'm going to write as u minus 4. And now we rewrite our whole integral. So I have u minus 4, that's the same as x, times the square root of u, and then dx is the same as du. This appears just as complicated as what I started with. But if you look carefully here, we can now deal with this. Right? I can't distribute the square root. Okay? I can't take the square root of x plus the square root of 4. That doesn't work. All right? And so I don't really have any way to break this guy up. Okay? But here I don't have that problem. Right? Now I'm just taking the square root of a single variable. Let's write it as u to the 1/2. Right? I can multiply this out and I get u to the 3/2 minus 4u to the 1/2 du. Take the antiderivative, add one of the exponent and divide, so I get 2/5 u to the 5/2 minus 4u to the 3/2 times 2/3 plus c. Let's clean up here a little bit and then we'll put our x's back. So 2/5 u to the 5/2 minus 8/3 u to the 3/2 plus c. And now finally we said u is x plus 4. So 2/5 x plus 4 to the 5/2 minus 8/3 x plus 4 to the 3/2 plus c. And that's in fact the antiderivative of x times the square root of x plus 4. It doesn't look at all obvious. And with type 3, they never look obvious. Okay. A type 3 problem is when we have to reuse the substitution. Okay. Reuse the substitution, in this case u equals x plus 4, to rewrite other parts of the integrand. All right. Let's see one last example of a type 3. Now one way to do this would be, of course, to multiply the whole thing out, but that's monstrous and completely unnecessary. So I'm going to take u to be the inside function. Du is the differential, so the derivative of t plus 5 is 1 times dt. Right, so I've got u to the 100 du, and I have this t squared left over. That makes it type 3. I've got to reuse the substitution to rewrite this last t squared here. Well, t is equal to u minus 5. And so we're going to take that and substitute it in where we see t. And so we get the integral of u minus 5 squared times u, which is t plus 5, to the 100 du. Right. Now this may not look immediately like we can do anything, right, but if you multiply this out, it becomes a polynomial, very high degree, but a polynomial, and then you can deal with it. What you can't do is some kind of strange product rule. There is no anti-differentiation product rule which says, here I can take the derivative of this and take the derivative of this. Right? Or take the antiderivative of each of these. It doesn't work like that. There's something called integration by parts, which you'll learn in second semester calculus, that's kind of like the product rule, but it doesn't, we don't have any nice shortcut here. Right? So what I'm going to do is multiply this out. Distribute the u to the 100 through. And then anti-differentiate. To u, it kind of looks like an A. So u to the 102 becomes u to the 103 over 103 minus 10u to the 102 over 102. And our last job is to go back to our original variable. In this case, u is equal to t plus 5. So we have t plus 5 to the 103 The thing about type 3 is they never, you look at the answer at the end and go, huh, you scratch your head. Because it's not at all obvious that what I have here really is the antiderivative of what we started with. It is, and it would require some careful differentiation and then algebra to show that it is. All right, but that's how it works. All right.